Good morning, guys. Today we're going to explore heat capacity and specific heat. You might want to have your calculator handy because there is going to be a little bit of math towards the end of the lesson, but on the bright side, it is a pretty short lesson today. So let's get started. Let's talk about what heat capacity is. Heat capacity and specific heat are similar in their definitions, but there is one difference in them, and we're going to talk about that difference in a second. But heat capacity is the amount of heat it takes to raise the temperature of a substance 1 degree C. And different substances will absorb heat differently at different rates, and that's just due to structural differences. So it does depend on the mass, because if I have something that is a larger mass, like for example, if I have a 5-gram sample of iron and a 1-gram sample of iron, the 5-gram sample of iron is going to have a higher heat capacity because it's going to take a lot more heat to raise the temperature of that sample versus a smaller 1-gram sample. So it does depend on mass and its chemical composition. So that means it's an extensive property. When mass changes, the heat capacity changes. So that's an extensive property, something we talked about way back in the beginning of the year, and here it is coming up again. So like I said, the greater the mass, the greater the heat capacity, and I mentioned a 5-gram sample of iron versus a 1-gram sample of iron. The 5-gram sample is going to have a higher heat capacity because it has a higher mass. There's more of it. And I also mentioned that different substances with the same mass will have different heat capacities. So that means if I'm looking at iron and I'm comparing that to the heat capacity of mercury, one is going to have a higher heat capacity than the other because they are different substances. But again, I can't compare those heat capacities between different substances unless I'm using the same mass. So here we have to look at it in terms of the same mass to be able to compare. There is a variation to this heat capacity that's a little bit more useful for calculations, and it's what we call the specific heat. So specific heat, you might see it, the symbol be C, a capital C, or you might see capital C with a little subscript there of P. And that is the specific heat. When I write it out, I'm usually going to write C sub P. Some textbooks will just write C. So you should be aware that you could see it both ways. So the specific heat is going to take into account mass. So it's the amount of heat it takes to raise the temperature of 1 gram. So anytime we talk about specific heat, it's that value is talking about a 1 gram sample of that particular substance. And we're going to raise it again 1 degree C, just like heat capacity did. Here it takes into account the mass, so that makes it an intensive property because the mass stays constant. And specific heats don't change. It's a physical property that actually can be used to identify the unknown substance. If you're trying to determine what substance you have, specific heat is something that you could use to identify it. Now, there is a table of specific heats, and you can see that table on the next slide. It's also in your textbook on page 508. So if I move on to the next slide, here's the table that's right out of your textbook. I apologize for the shadow. I took this late last night, and because I had the lights on in my kitchen, there's a little shadow there, so I apologize for that. But you can see that on this particular slide, we have specific heats either in joules per gram degree C or in calories per gram degree C, whichever unit we're using. Remember yesterday we talked about the energy units being joules or calories, and here they're giving you both in this particular table. One thing I want you to notice is I'm going to highlight water and I'm going to highlight aluminum. And you'll notice that water has a much higher specific heat than aluminum. This means it takes more energy to heat 1 gram of water than it takes to heat 1 gram of aluminum. That kind of makes sense when you think about when you heat water and the amount of time it takes to heat that water to boiling. It takes a long time to do that. Once it gets to that boiling point, when you turn off the heat, it takes a while for the water to get rid of the heat or to cool off. If you think about aluminum or aluminum foil, it doesn't take much to heat aluminum foil. If I put that over the burner, it's going to get hot pretty fast. When I take it off the burner, that aluminum is going to cool down really fast. It doesn't hold on to the heat. So the specific heat, it makes sense that it's so much lower. Water's going to take a lot more energy to heat that 1 gram versus aluminum. Now, to calculate specific heat, you need to know the heat, or Q, you need to know the mass of the substance, and you need to know the change in temperature, or the delta T. Delta T means change in temperature. We're going to take a look at how to use this equation on the next slide, but I do want to take a moment here to talk about the delta T. If you notice, I have down here some things listed like the Q and the M, and we're going to talk about delta T. But Q, we want to make sure it's in units of joules or calories. Most times we're going to see it in joules. We want to talk about the mass. That's always going to be in grams, so we're going to need to convert that to grams. And then delta T is always going to be in Celsius, degrees Celsius. When we calculate delta T, we're going to take the final temperature of the substance minus the initial temperature of the substance, and then that will give us the change in temperature. So we have to do a little extra math there to determine that. So let's take a look at how we would use this particular equation with an example from your textbook. So we're going to look at sample problem 17.1. It's found on page 510 in your textbook. And here is the problem. It says the temperature, and I'm going to highlight some things along the way that are important. The temperature of a 95.4 gram piece of copper, so that's important, increases from 25 degrees C to 48 degrees C, so that's important, when the copper absorbs 849 joules of heat. We want to know what the specific heat of the copper is. Remember, specific heat is C sub P. I wrote that kind of big, so let me write a little bit smaller so you can see the equation better. Let's look at what we know. I kind of highlighted it, but let's write it out. We know the mass is 95.4 grams. We know that Q, or heat, is 849 joules. That was given to us. That's the heat. And then the last thing is our delta T. We know that our final temperature was 48.0 degrees C, and our initial temperature was 25 degrees C, so we're going to subtract those two values, final minus initial, and that gives us 23 degrees C, and that's what we'll be using in our math problem. And we want to know specific heat. So we know what Q is. Q goes in the numerator. It's 849 joules. And in the denominator, we're going to put our mass, which is 95.4 grams. And we're going to multiply that by delta T, which we calculated to be 23.0 degrees C. When I do the math for this, I get 0.387. Now let's take a look at the units here. I have 3 units and nothing cancels, so I need to write all of those units. I'm also going to go to 3 sig figs because everything that was given in this problem, and we're multiplying and dividing here, was given to 3 sig figs. So I want my answer to be 3 sig figs. And my units here are going to be joules per gram times degree C. So we have a lot of units going on there, and we want to make sure that we put all of those units in. Let's talk about whether this makes sense. Copper is a metal, and just based on what I told you about aluminum on the last slide, copper will have a low specific heat because it's a metal. Most metals have low specific heats. They heat up quickly, they cool off quickly. They don't hold on to that heat. So our answer of 0.387 joules per gram degree C does seem reasonable. It's a pretty low number. Now I promised you a very short lesson today. I'm not even 11 minutes in, and the only thing that I need to tell you is your assignment for this evening. So let's take a look at the assignment. You're going to do some problems from your textbook. I want it to be handwritten, and I want you to submit it to the Dropbox. If you want to take a picture of it and submit it to the Dropbox that way, that's fine, but it is important that you handwrite it so I know that you did the assignment. We're going to be doing problems from two different places in your textbook. The first assignment is on page 510, where the example was given, and also the section assessment for 17.1, and you're doing numbers 3 through 11. Then you're going to go to page 535, and you're going to do numbers 42 to 44 and 46 to 47. And again, please handwrite that assignment, but I don't care if it's a picture of that assignment that you put into the Dropbox. I hope you enjoyed that lesson on heat capacity and specific heat. Tomorrow we're going to move on to calorimetry, and so please bring a calculator with you for that lesson, because we are going to be doing a little bit more math there than we did today. So I hope you guys are doing well. I know I say that every day at the end of my lessons, but I truly mean it, and I do really, really miss seeing your faces each day. It's very, very hard to do these lessons without an audience, and so I hope you're enjoying them. I hope that they're meaningful, and I will see you guys tomorrow when we talk about calorimetry. Have a great day.